Sustainable solutions are the future, and not just for us, but for the incredible creatures that share our planet, like the leatherback turtles. Each year, these gentle giants return to the shores of Maturo in my home country, Trinidad, laying eggs and continuing a cycle that has lasted for generations. But plastic pollution, especially microplastics, threatens their habitat. These tiny particles spread through the ocean, affecting the waters and the beaches where they nest. Protecting them means tackling these hidden pollutants. That's where chemistry comes in. By breaking down pollutants, reducing plastic waste, and targeting microplastics, science is helping safeguard ecosystems like Maturo. The key? Smarter, more efficient processes that drive real change. Ready to see how chemistry can help clean up our planet? This is Real Chem. To solve the planet's most pressing problems, we need to understand how to control chemical reactions. And one key property to control is the rate of the reaction. How long will our reaction take, and how can we influence its rate? To illustrate this, we're going into a hypothetical situation, but one that could happen. If scientists could develop a highly effective decomposing agent for microplastics, it could revolutionize water purification and environmental cleanup efforts, reducing plastic pollution and mitigating its impact on marine ecosystems and us. Envisioning how this can work will deepen our understanding of chemical kinetics and its role in solving real-world problems. Imagine we've created a decomposing agent that breaks down microplastics in water. We've proven it works, but now we need to determine the right amount to use. Too little, and the reaction will be too slow. Too much, and we waste the agent. This is where rate laws come in, and they help us predict how concentration affects reaction speed, ensuring efficiency. Let's start by writing this as a chemical reaction. The decomposing agent interacts with the microplastic, breaking it down into harmless products. But knowing the reaction equation isn't enough. We need to measure how fast it happens under different conditions. To tackle this, we must run some experiments. We will start with these initial concentrations of the microplastic and decomposing agent. We can monitor how these initial concentrations decrease over time by looking at a graph of concentration versus time. The slope at the start of the reaction tells us the initial rate. A steeper slope means a faster reaction, while a flatter slope indicates a slower reaction. We can also use a table to organize these results. In the first column, we record the initial concentration of the microplastic. In the second column, we record the concentration of the decomposing agent. And finally, in the third column, we list the initial rate as determined from our experiment. In general, increasing the concentration of reactants usually makes a reaction go faster. We'll examine how increasing the concentration of either the microplastic or the decomposing agent impacts the initial rate. First, we will focus on the microplastic. Let's double the initial concentration of the microplastic and redo our experiment. Notice, we've kept the decomposing agent concentration the same. The result? The reaction's initial rate doubles as well. Doubling the microplastic concentration doubles the initial reaction rate. This suggests a direct proportional relationship. We can write this as follows. In kinetics, we say that the reaction is first order with respect to the concentration of plastic. Now, let's focus on the decomposing agent. We'll keep the microplastic concentration constant, but now double the concentration of the decomposing agent. This time, the initial rate shows a more dramatic increase. It increases by a factor of 4. Increasing the concentration of the decomposing agent by a factor of 3 increases the initial rate by a factor of 9. In this case, the rate appears to be proportional to the square of the concentration. In kinetics, we say that the reaction is second order with respect to the agent concentration. Now let's put it all together. We found that the reaction is first order with respect to the microplastic and second order with respect to the decomposing agent. This gives us an equation for the overall rate law where K is a proportionality constant or rate constant. We can derive its value from our experimental data. Substituting our concentrations of the microplastic, the decomposing agent, and the initial rate tells us the value of K. This rate law is powerful because it allows us to predict the reaction rate under any conditions without needing additional experiments. More importantly, it enables us to determine the precise amount of decomposing agent needed to clean contaminated water efficiently, making it safe to drink. Why do we care about rate laws? They help us design smarter, more efficient processes. In our example, we explored a hypothetical scenario, but it mirrors how scientists solve real-world problems. Rate laws allow us to determine the right amount of reactant to make a process faster, more effective, and more sustainable. And sustainability isn't just an idea, it has real impact. By designing better chemical processes, we can reduce pollution, protect ecosystems, and ensure that leatherback turtles continue returning to Mataura shores for generations to come. That's the power of chemistry. Cool, right?